Hey everybody, I'd like to give us a look at a recent worksheet or today's worksheet, depending on where you're at. The worksheet was titled Acceleration Worksheet, and this had to do largely with free fall and some of the new acceleration equations. Okay, just to recap and make sure everybody's on the same page. So far, we've had three main acceleration equations. And we're going to look at using those today, and I'm going to help you out with a few of the problems on this worksheet so everybody's got a place to start. First of all, I'd like to write down the equations that we have. So first of all is the very first equation we learn with acceleration is that acceleration is change in velocity over change in time. Okay? Really, everything we're going to look at is a variation on this. For example, another equation had to do with how fast something is going when it's been accelerating, which was velocity, equals the initial velocity, or v0, plus acceleration times time. Okay? So that would be, if you know how fast you start, your acceleration, how long you're accelerating, you can figure out the final velocity. The other one had to figure out how far something went or where something's at, and that equation looked like this. Position equals initial position plus initial velocity times time plus 1/2 AT squared, where the acceleration is multiplied by the time, that same time from over here, but this time that time is squared. Okay, and we're going to use each of these three equations as we do some example problems. Okay, so first I'd like us to look at number 3. Okay, now as we go through each, I'd recommend just read each problem and then maybe pause the video, give yourself a minute to work on it, and then come back to the video. So for example, this says Alfred throws a batarang in the air straight up. At the top of its arc, what is the velocity of the batarang, and what is the acceleration experienced by the batarang? So, we're being asked to find velocity and acceleration, specifically at the top of its arc. Okay? At the top. That's key to remember. I specifically wanted to go over this because you need this answer to do a lot of the other problems. So when you throw something straight up in the air, we're focused on the top. We want to find velocity and we want to find acceleration. Now acceleration should be simple because, as we learned, acceleration here and here and here and here and here is all the same. Acceleration at any point when something is at free fall is the value of gravity. Acceleration is gravity, and gravity is negative 9.8 meters per second squared. Okay? That's anywhere. Once it's in free fall, nothing is affecting it except the value of gravity. Well, it's negative 9.8 meters per second squared. Now, velocity is different because think about it. In order for it to go up the arc and then come down somewhere, velocity has to equal 0 meters per second, and that spot is the top of its arc. So you're going to need to remember these as we go through today, that velocity at the top is 0 meters per second, and acceleration is negative 9.8 meters per second squared, no matter what. Now notice that this worksheet says show your work. There's some work, right? You need to show your work on all of these problems. All right, next one we're going to do is number 4. Let's read through the problem. Jed drops a 10-kilogram box off of the Eiffel Tower. After 4.6 seconds, how fast is the box moving? Neglect air resistance, meaning don't worry about it. Hint, is this a free fall problem? Well, is it? When Jed drops the box, is the only thing affecting it gravity? Yeah, it is. Okay, so we're being given It's a 10 kilogram box, 4.6 seconds. We want to know how fast is it going. I like to write a list of what I'm being given at the beginning of any specific problem. So for example, we're being given a mass, which is actually the letter M, of 10 kilograms. And we're being given a time of 4.6 seconds. Now, the question was, is this a free fall problem? Was the hint. Anytime you determine something is free fall like this, you should automatically go and write that acceleration is negative 9.8 meters per second squared. That's another given. Now, what's it being asked for? How fast? Is that time? Acceleration? No. We're being asked to find velocity. Okay? So that list right there, if you make that little list, you're going to be in a good spot to start any given problem. Okay? So we can look at our equations. We want to find velocity. Of our three equations, which one is going to be the best to find velocity? Well, this second one has velocity all on one side already. That's usually a good sign. Do we know the initial velocity? We'll come back to that. We know acceleration and time. Do we know initial velocity? If we know initial velocity, we can use it. Well, it says Jed drops this box. When you just drop something, think about how fast it's going right before you drop it. The answer is it's not. It's not going anywhere. And then you just let go, which means its initial velocity is 0. So we know everything. We can use the equation v equals v0 plus at. And this is all good work to be showing. Notice something that's not included in this equation. Mass. Mass was extra information. We don't need to know that in order to use this equation. We can go ahead and plug in everything. 0 meters per second for the initial velocity. Negative 9.8 meters per second squared for the acceleration. And 4.6 seconds for our time. 0 here doesn't matter, right? And it's just negative 9.8 meters per second squared times 4.6 seconds, which means I need a calculator. So we have negative 9.8 times 4.6, negative 45.08. So our velocity equals negative 45.08. And the unit of velocity is meters per second. Don't forget your units, people. Don't forget your units. Okay? Now, does this make sense? He dropped it, so it's going down, so we should have a negative velocity. There we go. So it does make some sense. We're going to skip down a bit and take a look at number 8 next. Let's read through it together. A cart is rolling along at a steady 11 meters per second. When it meets a slope, the cart accelerates at 1.6 meters per second squared as it rolls down the hill. How far from the top of the hill will the cart move in 6.6 seconds? So we're going to go through the same process where I'm going to underline what's given and then write out a little list. So it's going that fast, meets a slope, accelerates, and I have a time. So I'm being given a velocity, and it says it's rolling along, so this is like an initial velocity of 11 meters per second. I've been given an acceleration of 1.6 meters per second squared, and I'm being given a time of 6.6 seconds. That's all it's really been given, and it's asking how far. Oh, that's bad. I'm being asked how far. Okay? How far? That's not a velocity. That's not a time or acceleration. That is a distance. So, really and truly, we're going to be using that x in this case. Now, I said this list is useful. We need to find something with x in it, maybe using these other variables. So we go back to our equations. And because we're trying to find position, how far something goes, which would be a change in position, really, we're going to use this equation right here, where x0 is going to be 0, because we're going to assume he starts at the origin. But otherwise, we have everything else in that equation. So I'm going to rewrite my equation here. X equals x0 plus v0t plus 1/2 at squared. And like I said, this is all good work to be showing. We said that x0 was going to be 0 meters because we're assuming it starts at the origin. So now let's plug it all in. Plug it in like a Glade plugin. X equals 0 plus initial velocity was 11 times our time of 6.6 plus 1/2 our acceleration of 1.6 times our time of 6.6 seconds squared, though. Now, notice this is the equation we were taught with free fall, but it's useful in all sorts of acceleration problems as well. Let's go ahead and simplify a bit. I'm going to just work out this back term where I'm going to do 6.6 squared times 1.6 times 1/2. So let's pull out that calculator again. So I need 6.6 squared, right? And so I'm just going to do 6.6 times 6.6, same thing. And it's times 1.6, right? Times 1/2. All right. And so I end up with 34.848. Let's write that in. So now I simplified this. 34.848. And I'm going to do this 11 times 6.6 next as well. 72.6. So I really just simplified this. So there's where we're at. And now I can just add up those two numbers. 34.848. 107 point, and we didn't go to so many decimals in the problem, so we can just go 107.4. X equals 107.4. Now, how far, that's a position, so our unit is meters. If you don't include your units in your answer, you should lose points. That's my opinion. There you go. That's how far this cart went after 6.6 seconds of accelerating down a hill. We'll do one more. Number 12 says Max throws a tennis ball straight up, 26 meters per second. That's like 60 miles an hour. How long does it take the ball to reach the top of its arc? Oh man, we're not being given a whole lot here. We're given this velocity as straight up, so it says he throws it that fast. So that's an initial velocity of 26 meters per second. And I want to know how long it takes. How long? That's a time. So that would seem like it's all that's being given to you, right? Velocity asking you for time. It's not quite. First, is this a free fall problem? Well, tennis ball thrown up at the top of its arc, which is the specific point we're talking about. Is it in free fall? Sure. Which means, like I mentioned in an earlier problem, you should be writing that acceleration is negative 9.8 meters per second squared. Right? So, something else that I mentioned was super important. How long does it take to reach the top of its arc? So we have V0t and A, or we're trying to find time. So the equation that would make the most sense to us is the second one. We have V0, we have A, we're looking for T. If we could have the final velocity or the velocity at the top of the arc, we could use this equation. Well, we do. This problem, we talked about how important it is to remember that the velocity at the top of an arc is 0. Okay? This is a very, very useful concept with free fall. Okay? So we will note that the velocity at the point we're talking about is 0. Well, now we can use this equation of v equals v0 plus a t. Knowing that the velocity at the top is 0, our initial velocity is 26 meters per second. Our acceleration is negative 9.8 meters per second squared. And we're looking for time. You got to do a little algebra here because we want to get this time by itself. And the time is attached to the negative 9.8. There's a separate term here, this 26. This 26 is a positive 26, and there's some addition going on. To move it over, we would subtract 26 from both sides. And that, this is going to get a little messy, would lead over here. Negative 26 meters per second equals negative 9.8 meters per second squared times time. Hopefully it's obvious to you that to get time by itself, we're going to have to divide because these two things are being multiplied. So we divide by negative 9.8 meters per second squared. Right? So pull up our calculator. And we would do negative 26, and a negative divided by a negative is a positive. So keep that in mind. So negative 26 negative divided by 9.8 negative gets you a positive 2.7. We only have one decimal place, so let's just do 2.7. So time equals 2.7. The unit of time is seconds. This tells you how long it takes to get to the top of its arc. Believe it or not, the time it takes to get to the top is actually half of the total time. So if you had to know how long it takes to do the whole arc, you would know that it is double that value, so long as you're going to the same height. Okay. So, which number 14 kind of does that, but it wants you to go to the ground, which is an extra 2 meters. So you got to do a little more math to get to that. But that's been a few example problems. I've been Mr. Peritano trying to give you some help. If you didn't know who this was talking, feel free to email me or your teacher if you need a little extra assistance with the acceleration worksheet. Hopefully that cleared up a bit of confusion, and I will see y'all later.